Now that we know how to write the equation of a line in space, in other words, 3 dimensions, we can start talking about problems that involve lines. For example, maybe we want to know how far away a line is from some point in space. Now, there are applications for this. If you are a land surveyor or if you do any kind of work around a home, you might need to make sure that something that you're installing is a particular distance away from a roof line, for example. And so if you have a line representing the roof line, then the point M, we need to know how far away that is from the roof line. So let's try some problems. We have a line on the screen, and any line must have a known point and a parallel vector. No matter which version of a line equation that you use, you'll always be able to extract from that a point P and the vector that the line is parallel to, V. To figure out the distance from our line to the point M, the first thing we're going to do is generate a vector that connects the point P on the line to the point M, which is not on the line. Next, I'm going to arrange the vectors, V and that vector PM that we just created, so that they share the same initial point. Remember, we can move vectors around without changing the value of the vector. We just aren't allowed to twist it. So I just slid the vector V over so that the vectors green and blue are sharing the same initial point. And then we're going to create a perpendicular, a line segment from M down to the line L. And that's going to create a right triangle for us. Now that red line that we're looking for, the red dashed line, that is the actual path that we're trying to calculate the distance for. Notice that if I had picked different points for P on the line, maybe I had freedom to choose whatever I wanted. If I had picked this for P and then calculated the vector between P and M, the distance is still going to be the same, no matter which point I used. And often I see students say, well, why didn't we just pick this point P and calculate the distance between these 2 points? And that would be a great idea if we had a way of finding how to find that point P. We don't know how to find the point that's perfectly on the line. We don't know which parameter value to use. So we have to just take any point that we can find, and we'll assume that it's not that special point that we wish we knew. It's a safer assumption. So we pick some point P, generate a vector between P and M, connect the vector V to the point P so that we have a nice little right triangle formed in our diagram. The reason why we want to do that is so that we can take this higher level problem and reduce it down to something that we know very well. For example, area of a triangle. We can see that the blue vector, the direction from the green vector, and the red dashed line, they all make a nice right triangle. And the area of that type of triangle is simply 1/2 base times height. But also, we've worked with the area of a triangle using vectors in the last section. So remember that the area of a triangle that's formed between vectors is simply 1/2 times the absolute value of the cross product between those vectors. And if we look at our picture, we can see that the vector PM and the vector V are set up just like they were when we talked about area between 2 vectors. We're going to use the magnitude of the vector to represent the base of our triangle. So from the point P to the tip of the vector V, we're going to make the triangle like this. It's not a right triangle, but don't worry, we don't need it to be a right triangle to use the formulas that we know. And then from there we can change our picture to say that green vector has a length equal to the magnitude of V. The blue vector, if I wanted to write out the length of that, I would write magnitude of PM. Maybe we need that, maybe we don't. Since we're using the vector v and the vector pm to make a triangle, those are the two vectors that we would plug into the cross product for calculating area. So on the left side of our area of a triangle formula, we replace the words area of a triangle with how we calculate area in Calc 3 using our two vectors. So 1/2 cross product between the blue and the green vector, and then absolute value of that cross product, because areas should not be negative. And then on the right-hand side, we've replaced what we were calling the base in the initial area of a triangle equation. We've replaced it with the actual value for the base, which is magnitude v. The only thing we do not know in this equation is the height, and that's exactly what we're looking for. The height is this red dashed line. So, because it's the only unknown in the equation, we can solve this for that value. We need to multiply both sides of our equation by 2. That will get rid of the 1/2. And then we need to divide by the magnitude v. That will leave us with the absolute value or magnitude of the cross product between the blue and the green vector divided by the magnitude of the green vector. That will give us our height, which we will call the distance. Now that we've made this image and we've come up with the shortcut formula using vectors to find the distance between the point and the line, let's practice. So in this problem on the right side of the screen, we're asked to find the distance from the point M at 1, 1, 3 to the line L given by the symmetric equations that we see. Now, in order for us to solve this problem, we first have to extract all the given information out of the line L. The equation of the line L is given in symmetric form. So let's make it look a little bit more like that symmetric setup. We'll give the third part of the equality a denominator of 1. And then instead of y plus 1 here, remember that would really be like y minus -1. From here, we can tell that the point P at x0, y0, z0, let's color code this, has the points 3, -1, 3. So the point P is at 3, -1, 3. And then the vector v, remember that those components come from the denominator, so the components of v will be 4, 2, and 1. Now that we have that, we can start to calculate the vector pm, and then we can do the cross product, find the magnitude, and so on. So let's go ahead and find the vector pm next. M is the terminal point, P is the initial point, so doing our vector subtraction, we get -2, +2, 0 for pm. We have the vector v, so we can calculate the cross product there. Now remember that for calculating the magnitude of a cross product, we have a shortcut, kind of. That shortcut is only really a shortcut if you know the angle between your vectors. And since we don't, we're not going to use that shortcut. Instead, we're going to calculate the cross product, then we'll find the magnitude of that vector that comes out of our cross product. Set up our 3 by 3 determinant matrix with PM in the middle row, V in the bottom row, and then we'll go ahead and evaluate that. Next, we'll find the magnitude of that vector, taking each of the components, squaring them, then add them up. and simplifying if possible. All right, next we need to find the magnitude of v. Remember that our vector v has components 4, 2, and positive 1. Square the components, add them up, square root them. And now we're ready to plug everything into our distance formula, and it looks like I have just enough room to do that right here. Our distance is going to be the magnitude of the cross product, which is 2 root 38, divided by the magnitude of the vector v, which is root 21. And we can type that into our calculator if we want to have more intuitive feel of what that distance is. But really, 2 root 38 over root 21, that's the exact answer. We don't like to approximate sometimes because, well, it's not a better answer in terms of being precise. But sometimes we need to approximate because when I tell you to go 2 root 38 over root 21 feet away from me, you might say, I have no idea what that means. Can you give me like a range between some whole numbers? And then I would say, yeah, I'm talking about like 2.7 feet. Figure it out. Exact answers are great, but they're hard to interpret, so we use approximations for interpretation. And even if I were to extend this decimal, that doesn't make it exact. Adding more digits after the decimal is still an approximation. It's just a more precise approximation. All right, so we found the distance from the point to the line. So from the point M to the line L, it's approximately 2.7 units away, but it's exactly 2 root 38 divided by root 21 units away.